This video is going to be a bit of a refresher for the enols and enolates that we've already discussed in recitation, that you've discussed in class as well. Just because it's been a while, because of spring break, I thought it might be useful. Obviously, there's the bare bones of how this all goes down, where you have some carbonyl. And at these locations, one carbon away from the base of the carbonyl is denoted by Greek nomenclature. The locations of these carbons are called alpha, beta, gamma, and delta. And the one that we care about for these upcoming chapters is this alpha carbon right here. Because as you've learned, this alpha carbon is fairly acidic due to the resonance nature of its conjugate base, where if we were to deprotonate it with some base and form the conjugate base, we have something that is resonance stabilized. And that's going to form this enolate here. Actually form the proper structure. So there's your enolate, being an alkene, an alcohol, enolate, where we have the deprotonated version of that alcohol. Whereas if we did a bit of work up here, we could obviously turn that into this structure here. But in order for it to want to form this, because as this currently is, it's going to want to stay in this version. That's far more stable. If we can add some type of stability to the enolate structure, then we're in better shape to form it. So for example, if I was to instead maybe try deprotonating this, would probably take off this one because it has more resonance. You've seen how the deprotonation works, and we can go ahead and form that, and that's going to form a resonance structure, which can then in turn either pop up on this oxygen, or the negative charge can move up onto this oxygen here. And this is actually going to want to form and stay in the enolate structure here. So this is going to be 70 to 90% in this form, as opposed to the non-enolate form. So depending on the type of beginning carbonyl that we're working with, it's going to determine the bases that we use. Because the more stabilized the conjugate base we have, the less strong or weaker of a base that will be necessary. So for example, for the first example we showed here, we would say that sodium hydroxide typically isn't going to be sufficient to deprotonate this entirely. It's going to want to form and stay in that direction as opposed to moving in this direction. Whereas with something like this is fairly acidic. And consequently, we can have a sodium hydroxide here, which will work fairly well to form this structure. Something like this, a single carbonyl is going to want a base like LDA, which I'll go through the structure momentarily, or NaH. NaH is wonderful. It's my favorite because it's just going to form molecular hydrogen, bubble off. LDA is a very strong base. Whereas something like this, you can still use LDA, NaH just fine, because if it's going to deprotonate this, of course it's going to deprotonate this. But we can go ahead and use NaOH or some other methylate or whatever. They'll all work for this situation here. And this is what we're going to be working with primarily. So as opposed to the carboxylic acid derivatives chapter, we were focusing on how the carbonyl here could be our electrophile. Now what we are going to focus on is that special alpha carbon right here, and how it can be the nucleophile. So we're still kind of talking about the carbonyl itself, but rather we're focusing on the molecule that the carbonyl is attached to, how we can convert it into a nucleophile. Whereas in the past chapter, we were focusing on how it was going to be our electrophile. And so while these were substitutions, these are going to be additions, because we're going to go ahead and use this as a nucleophile to attack something with a leaving group usually, and we're going to add on this piece onto our nucleophile that we're talking about. And so the first example of that type of reaction is going to be our haloform reaction, which I hope you remember Ty talking about almost dying from forming chloroform, but now you should know it's fairly simple to do. So once we've formed that enolate, I like to show it in this form, and let's actually talk about that for a second. So obviously there's the two resonance forms here, where it can either be shown like that, or it can be shown this way. And in this form, you can see how we have kind of two quote-unquote nucleophiles here, where we can either have this oxygen be the nucleophile, which is going to be called an O attack, or the alkene here, or rather this negative charge on the carbon will attack, and that's of course going to be called a C attack. And more times than not, the C attack is what's going to happen. And the true mechanism for that should be where I'm just going to draw some random electrophile here. The true attack for that is we start from this form and we push these electrons down. Of course, we always push electrons 2 in, 2 out, kick this out, and this is a true C attack mechanism. But for all intents and purposes, it's a lot easier to go ahead and just draw it in this form and show this happening in this form, which is still a C attack, and you'll see Klein talks about that as well. But this is sufficient. Obviously, in your upcoming exams, multiple choice and mechanisms, you're not going to be drawing any, so that's not something that really to be concerned for. But for future standardized exams, be aware that they could show it in either form, this being the true, this being more common, but they're one and the same. One's just shorthand. Now, again, talking about that haloform reaction, the idea is we're going to add halogens. The halogens, we're going to add them to the alpha carbon position. There's a base catalyze and an acid catalyze mechanism. The base catalyze is, you've already seen how we've got there. This is base catalyze, using a base to get to this structure, and we're going to attack our electrophile, which is going to be some molecular halogen. Br, or bromine, very common. It's going to come in here, kick this out, and of course it's just going to pop that sucker right on there. And bada bing, bada boom. And we've added a bromine into the alpha carbon position. And this can also be done in an acid catalyzed formation, which instead of starting with this structure, we instead, so this, let's just put base catalyzed. So the acid catalyzed instead is, we're going to form this structure except in acidic conditions. And as you know, we don't form negative charges, but instead we always form positive charges in acidic conditions. And this instead is going to be our nucleophile. And if we attack the same electrophile, we're just going to hit that guy and going to end up forming the same thing after a bit of workup, which you can figure out in your heads there. It's going to form the same structure. And the difficulty with the haloform reaction is you might notice that we've added an electron withdrawing group into this alpha carbon position. So this bromine, because of its induction, is going to be pulling electron density even further away from this hydrogen that's still there. And consequently, it's now even more partial positive, even more acidic. It needs electrons even worse than before. And as Klein mentions, it's very difficult to get a monobromine addition here, or a monohalogen of any type, because what it likes to happen is, or what it likes to do is replace all of those hydrogens that we have available there eventually with as many halogens as we have in that beaker to work with. And how this starts to change the reactivity is right here, we would stop because we've run out of hydrogens. But let's say we had instead started with, acetone, and we've got 3 hydrogens here work with, and those can, through the haloform reaction, be replaced with 3 leaving groups. And this, I hope you recognize, is a wonderful leaving group. This isn't quite yet there, but this is actually going to stabilize the negative charge sufficiently that we are actually going to go ahead and be able to kick that sucker off in such a way that this can go ahead and just leave, and that's going to form CBr3 minus. And normally we don't like to see a negative charge on a carbon, but 3 bromines is more than enough to go ahead and stabilize that. Now, of course, these aren't just going to leave, but rather we're going to want some nucleophile to incentivize this pushing of electrons, and what's commonly used, because it's so useful to form carboxylic acids, is we're going to use some hydroxide, and that's going to kick this up, which 1, 2, and then that's going to come back down and finish out that and kick off the leaving group. And of course, we're going to form our carboxylic acid. I kind of showed that to you backwards. Sorry about that. And usually we're going to have some kind of acidic workup, because you all know by now this is very acidic. And looky here, we've got ourselves a base, and that's going to pick up that hydrogen and form the carboxylate ion. And with a little bit of acidic workup, it's just going to go ahead and form our carboxylic acid along with bromoform here. And if you started with chlorines, that forms the infamous chloroform. So let's take a step back now and talk about the location in which the halogen likes to add to. Now, as you've learned, we like to go through the most stable intermediate. We always focus on that in organic chemistry. That's what makes a good organic chemist, is thinking in your head as you're doing the mechanism or thinking about the product, what intermediate am I going through? So right out of the book, Klein gives a wonderful example where if we start instead with this and we react it, let's do the acidic workup. And our halogen of choice, I'm just going to put X here for any halogen. And as you can imagine, eventually at some point, we're going to form some intermediates. And one of them being this one right here, or the other one being, we're going to form the alkene over on this side. Right, because we could either depronate this alpha carbon or this alpha carbon. And as you've learned, a more substituted alkene is more stable. So you can imagine, or you can see that this is tetrasubstituted, whereas this one is trisubstituted. So this is more stable. So this is going to be our major product. We're going to focus on this intermediate pathway because it's going to form the major product. And so coincidentally, we're going to go ahead and ignore this for our major products, and the bromine almost always is going to add on the side where we are more substituted. Okay, so Ty mentioned that you're going to need to know the names of these reactions, and that's entirely true, especially so now that we're moving to multiple choice formats. That's going to be pretty prevalent now, as well as on future standardized exams, MCAT, DAT, BCAT, and hopefully, ideally, in the future, ACS. Not this semester, unfortunately. I'm very sorry about that, but in the future if you are able to take it. The Hell-Volhard-Zelinsky, I'm probably saying that wrong, but the Hell-Volhard, let's see, Zelinsky. Oh, you think I spelled the part right? That has half my name in it. Is, well, they say believed to occur. They only say that when, not enough research is out, but we know that this is definitely, if you push the electrons, this is the pathway in which it takes place. But it starts with the carboxylic acid. And the end game of this reaction is a way in which you can add an R group of your choice right here. And so I'm going to put it in blue here, but we want to get that on there. But as we learned earlier, this is used for nucleophilic substitution, but this can't be used for addition because this is the more acidic proton. We're not going to be able to deprotonate this as long as this is on there. So what we need to do is we need to get rid of this OH, replace it with something so that we can in turn add this, and then just convert it right back to the carboxylic acid. The last unit prepared you very well with a slew of methods in order to do that. The Hell-Volhard-Zelinsky reaction specifically, though, is going to use PBr3. This is the reagent that I will always use. And just as a refresher, because I know it's been a while, the mechanism here is this is going to become a wonderful leaving group for us. And so what we're going to do is we're going to go ahead and push these electrons over and cause this to hit this electrophile, which is going to kick off a bromine. And it's going to form some R here. And we still have the R there. And now we've got this. And connected the phosphorus with the two bromines. And I hope you can recognize that this is a really good leaving group. So, of course, coincidentally, the bromine that's formed is going to perform a substitution right here. And I don't need to waste you guys' time with what you already know, but that's eventually going to kick off that leaving group. Place the bromine on there. And the leaving group that we just formed is actually going to serve to come in and what a miss, huh? Going to come in and deprotonate this for us and turn form our acyl halide. Okay, and so that's going to be kind of the first step of our Hell-Volhard-Zelinsky. And then through some tautomerization, which is all over the book about 1,000 times, so it's a mechanism I'm not going to show you. But you're welcome to look up if you need a refresher. It's going to form this structure right here. And note that the alkene is going to form where that alpha carbon is. It's going to be between the base of the carbonyl and that alpha carbon. I hope you don't put it on this side. And then what we're going to do is react that with our electrophile from the haloform reaction, which is, molecular halogen. We're going to stick with bromine here because that's what Hell-Volhard-Zelinsky, that troop used, I guess. And that's going to halogenate the alpha carbon position. Okay. I'm realizing I think I misspoke. I think I mentioned about this allows the Hell-Volhard-Zelinsky reaction's purpose is to put an R group on here, but I meant to say that it's going to allow us to add a halogen there. The idea, though, is it's going to allow us to use this as our nucleophile. Despite having a carboxylic acid, we got to move away from the carboxylic acid. So I apologize. Not an R group. The Hell-Volhard-Zelinsky is specifically for adding halogens to that alpha carbon position. So then we have our aldol reactions, and they are as they sound. They're aldehydes and alcohols attacking and working together. As Ty mentioned in class, if we start with a ketone, it should be called a ketol, but they're all grouped under this umbrella name of aldol. But we don't really use ketol reactions, or we do, but we don't use that name. And so, true to the name, I'm going to go ahead and start with the aldehyde first. And let's say we just have a beaker of aldehydes, and we drip in some LDA, and drop by drop. And that's, of course, going to form the enolate here, yeah? And every time we form one of these, it's going to immediately want to react with its bros in the same beaker, because this is nucleophile with electrophile. It's not going to wait to form. And that's going to form 1, 2, 3, 4 carbons. See, I've got 1, 2, 3, 4. So I better have 4 in my product. And for me, it's easy. Sometimes it's hard to see how these form. I always make mistakes when I have more complicated substituents on the left or right here. But I like to keep, as it looks, you know, I'll have this guy on the right, and so I'll leave him as is. And this arrow right here is this bond being formed, okay? So if that's the bond being formed, I want to make sure I keep this hydrogen, and I just like to kind of move it down and out of the way, but I haven't lost it. And then, of course, this is going to go up here. And, you know, through some type of workup, we go ahead and protonate it. And I'm going to grab the eraser. Not very fast at that part yet. And we protonate it. Now, let's look at it as if we start with acetone. So again, we drip in LDA. And we form this enolate right here. And this is going to want to go and hit that guy. And again, using the same method I just talked to you about, I like to keep him on the right. Again, you don't have to do it this way. This is just how I can see it best. But it comes in, attacks that, and this bond, again, is this bond being formed right here is this arrow, this movement of electrons. To that, I need to make sure I don't lose this carbon. So again, I'm just going to move it down and out of the way. You can imagine if this was just some R group, all you got to do is draw your R group down here. And we go ahead and move this up. But again, with workup, we form the aldol. And let's say plus workup here, you know, some acid workup or whatever. And we form the aldol. The common mistakes here is the incorrect placement or loss of this R group that was over here, or hydrogen, or whatever it is you start with. You know, if this is your LR, your R group on the left, and then it'll go here and whatever. But just make sure you don't. That's a common mistake, so watch out for that. And finally, we want to make sure that we know how to condense these. So what we have is called an aldol condensation. And as was mentioned in your guys' class, someone asked the question, well, how do you stop it here? And in reality, all of this is crap chemistry, yeah? So this isn't very incentivized to move in this direction. It might form like this, where it's going to want to stay in this form. So you got to make sure you can go backwards. Lots of standardized tests love to have you have this and take it backwards. But what's really going to happen is you're going to have your base still in the beaker typically, and that's going to cause this to condense and kick off water, because when you have condensation, you form water droplets, right? And that's the idea of what's going to happen here. So let's say we still have our base, and I'm just going to use sodium hydroxide because that's what Klein loves to use. And now, which alpha carbon am I going to deprotonate? I've got this one. If I tautomerize this, I've got this one. I've also got this one. I hope you can see that this is the most acidic. 1. And so, of course, this is the one that we're going to want to deprotonate, right? And so we're going to go ahead and deprotonate that, form the enolates. In reality, this will resonate up. But again, I'm just showing you the shorthand notation here that is frequently used. Okay. And since we have sodium hydroxide that we're working with, it's no big deal to go ahead and use sodium hydroxide as our leaving group. This is actually going to come in and kick it off, forming this conjugated pi system with our group. Just going to point it up now. And this is going to be favored. This is where most of our major product is going to go. It's very uncommon to get it to stop here. Standardized exams sometimes do ask, what's the product of this aldol, and they'll never show this product itself, but rather they'll just show these ones. But just be aware that if you're in the lab, this is what you're typically going to form as the condensation reaction. Because of course this is more stable. What we have here is a conjugated pi system, and as you've learned, that's far more stable. Okay, so this stuttery mess was my first attempt at this format of lecture. I apologize, it was a bit haphazard and kind of messy. I imagine it'll get better as I get more practice. But if you've got any questions or comments, please let me know. And just remember that this was just meant to be kind of a refresher of the basics of what was covered before spring break. I didn't go into the specifics, and I probably won't. I'm going to focus on the new content from here on out. So upcoming lectures will be more pointed and specific on the new upcoming stuff.